Okay, before we start off, some housekeeping announcements. Quiz Friday. It should be, 15, 20 minutes-ish. So just a couple of short, really quick questions. And so then obviously the difficulty of the questions is going to be proportional to the time. Whereas on the exam, it might be testing the same concepts, but they'll be much lengthier type problems. Homework 1 solutions have been posted. We'll try and get those graded either this afternoon or by tomorrow, so you'll have those back. But for the most part, don't count on the graded homework to give you a tremendous amount of insight into how to solve the problems, because the solutions are posted. And so then it should just be a matter of kind of looking over the solutions to make sure that your solutions match with the ones I had written down. So when the homeworks are graded, they're not going to be very detailed, saying, oh, on page 7, you lost half a point here for something like that, because it's, you've got the solutions already. Homework 2 has been posted, 6 questions. I wanted to go over them a little bit. So one, I think, is, well, first of all, are there any questions before I go over some of the concepts? I've seen a lot of people have the homework in front of them. One is talking about deriving some ideal gas relationships. Pretty straightforward. More or less just plug in the ideal gas law for the different partial derivatives and rearrange and solve, and the answers are right there. You just have to get from point A to point B. Question 2 talks about an isentropic compression of a gas. This is basically using the energy and entropy balances to, more or less an entropy balance to figure out the path that a gas has to take in order for S to equal to, delta S equal to 0. This is what's going to happen when you pump or pressurize something, or you run a turbine or a compressor. You want to run the material through an isentropic path, so you have to be very careful control over the temperature and pressure profile, which makes those things difficult to develop. Question 3 and 4 and 5, they all kind of are derivations. So in question 3, we're asking to show that in the transition from a liquid to a vapor, this is what we skipped over in class. I want you to demonstrate that the same approach going from a liquid to a vapor is equal to this approach here. The hint that I gave is to go through using this term Z. The reason why I want to cover this just a little bit is because it'll come up quite frequently. Depending on how you do number 4, it might pop up, and number 5, it may also pop up as well. Well, not necessarily this derivative, but just the concept of using the compressibility factor. Now the reason why, if you look at number 5, everyone has the homework in front, you're asked to derive an expression for the van der Waals fluid's fugacity. And this is something that you're going to be using in question 6. And we got some other terms here. Let's see, minus ln c v. I'll just write the whole thing out. So, the compressibility factor is useful for a lot of the thermodynamic relationships that we'll be using, because oftentimes we'll see things that look like this here, where we'll have the compressibility factor of the vapor minus 1 minus the compressibility factor. The reasoning behind this is that most all of the relationships that we're going to be doing or developing, we're going to go through an ideal gas state. So oftentimes, in the case of fugacity, the fugacity, if we recall, is effectively a scaled version of the Gibbs departure function, meaning that we take the difference between the Gibbs free energy of a real fluid minus the Gibbs free energy of the ideal gas, and then we normalize it by 1 over RT and take the natural log of the exponential of it, right? So when we go through and we substitute in the compressibility factor, when we see terms here like z of v minus 1, that means this is the PV of the real fluid divided by the RT minus the PV over RT of an ideal gas, which makes it very easy for us to say that's just 1. Same thing here, we have natural log of z. The natural log of 1 is 0, so it goes away. So that's why you oftentimes see expressions written like that in terms of the compressibility factor, is because when you have the compressibility factor and you consider an ideal gas, it goes to 1, so it's kind of a nice compact way to write the equation, and it also gets rid of the ideal gas state and turns that whole complexity into just 1. So that's why you see that oftentimes. Now that may come up in 3, 4, and 5. 4, it all depends on how you do it, but z may come up in 4. Now, on number 4, I've written it a little bit confusing. So the departure function is a relatively, hopefully straightforward concept where the departure function for the internal energy is the actual fluid internal energy minus the internal energy of an ideal gas. Now, what I'm looking for here, that I don't think I really explicitly made it clear in question 4, I'm really looking for the departure function for varying dt equals 0 with changing pressure or volume. Now the idea behind this is more or less the last part of the problem. So in this I ask you to calculate the departure function and the U, H, and S for ammonia transitioning from an ideal gas state at temperature equals 0 to a pressure of equals to 10 atmospheres. So the idea here is I want you to first derive the expressions using the van der Waals equation of state and then apply it. You'll also notice that on question 6, we're using the van der Waals fluid to do the vapor-liquid equilibrium of ammonia. So what's going to happen then is on homework 3, we're going to be combining these together and basically developing an entire phase diagram all the way from some arbitrarily low temperature all the way to the critical point. In addition to doing the phase diagram, getting the vapor pressure, the saturation temperature, saturation pressure, volume of the liquid, volume of the vapor, we're also going to be calculating the internal energy, the enthalpy, and the entropy. So effectively, using only the van der Waals equation of state, which only requires us knowing what the critical point of the system is, plus the heat capacity of an ideal gas, we're going to be reconstructing the entire, effectively, steam tables. And we're going to be developing it for ammonia, only using basically 2 pieces of information: critical point and ideal gas heat capacity. So that is why all these questions are kind of listed how they are. And so in homework 3, one of the big problems is going to be constructing this whole big phase diagram, and also the enthalpy tables, and the entropy tables, and the internal energy tables, and the density. So I would take these problems very seriously, because you want to make sure that you get it right, you understand how to apply it, especially that's doubly so in question 6. Because you may be able to do this problem 6 right here by hand, where I'm asking you to basically calculate the fugacities and then calculate the vapor pressure. I'm basically easing you into calculating the vapor-liquid equilibrium in different stages. What's the fugacity of the vapor? What phase is it in? And then the last part, part D of question 6, says, vapor-liquid equilibrium, we're in coexistence. What's the fugacity of the gas and liquid phase? What's the system pressure? So I'm asking you to solve for the vapor pressure, which we can do so using the expression that you'll develop in question 5. What I will be asking, though, in homework 3 involves solving question 6, but in 5 degrees Celsius increments for like 150 degrees. So if you write it to do it manually in Excel, you may struggle to repeat it again and again and again and again and again. So whatever it takes for you to solve this problem or question 6 on this homework, just be aware that you may have to find a way to automate that calculation process to expand it to build an entire table. So just keep that in mind. So the last comment here on question 4, that's why I want to have this all on the video so we can go back and review it. I say that I'm looking for the departure functions, U, D as a function of temperature and pressure, and then H, departure, enthalpy departure as a function of temperature and pressure, and the entropy departure as a function of temperature and pressure. That's not actually what I ended up solving, so this is a little confusing. In the book, they have expressions here for these kind of departure functions, or you can kind of piece them together a little bit. But for the most part, on your equation sheet, we have expressions for du, dh, oops, not dv, and ds. Now, the internal energy one is relatively straightforward. That one already is a function, it's like cv dt, plus there's some big integral dv. They have this expression's equivalent for change in enthalpy in chapter 6 of the book. Or we can just say that H is defined as U minus PV. So as soon as you solve for the enthalpy, the internal energy departure function, you can just recalculate it with enthalpy. So different ways to do this. But the key thing, though, is that the internal energy expression is going to be your most useful one to work with, because it's using specific volume as the independent variable. The van der Waals equation of state has specific volume as an independent variable. So when you need to go through the manipulations of the differentiation and the integration here, you'll want to have the explicit volume expression. If that makes sense. So when it comes to actually solving for these here, it's going to be a little bit roundabout. So in this case, we say the pressure is equal to 10 atmospheres. But then we need to use the van der Waals equation of state to let us know what the specific volume is, so that we can then substitute it into these expressions here. So when I say as a function of pressure, I didn't really actually mean as a function of pressure. You'll just have to use the pressure through the van der Waals equation to get the specific volume. I don't think it's going to be exceptionally trivial, and it may not even be feasible, to get explicit equations where pressure is the independent volume, independent variable. So hopefully everything is straightforward. Most of this is just hints. The question 4 is a clarification of what I'm looking for. But the purpose behind it is that it's sort of a warm-up problem to get us to the point where we're going to be solving all the vapor-liquid equilibrium, all the enthalpy tables for a fluid using limited pieces of information. Sound good? Any questions?
I have a question about some of the other things, if I can. Question 1, the first 4 parts I thought were pretty easy.
Yep.
But the last part, I was having trouble figuring out how to substitute that in.
So the part E, I believe I manipulated C and D to get to that point.
So you took the 2 equations, C and D, that you got.
Yes, I manipulated those two to sort of get rid of the temperature dependence and substitute in volume or pressure dependence. I think you could probably do the same thing as if you manipulated the expressions up top and then solved for dt and set them equivalent. And then integrated those expressions, or you could just work with the expressions C and D that are derived. The 2 different ds expressions. But yeah, that one's probably the trickiest one. But that was the path forward I took, was to manipulate the expressions I had already derived. Any other questions? So this one's not particularly, there's a decent amount of questions, but each of them are relatively straightforward. So the homework is due a week from today. Okay. So as a roadmap, today and a little bit spilling over into tomorrow, we're basically going to be wrapping up single component systems. So Friday, Monday, and next week, we're going to be talking about multi-component systems and the additional complexity that's involved through there. Once we finish up describing the fundamentals of multi-component systems, we have basically completely rederived all of classical thermodynamics. So in about a little over 4 weeks, we've more or less derived everything. Now, we haven't done as many application problems, which is reserved more so for the homework, right? But the key thing is, for the quizzes and the exams, when we have expressions, for changes in internal energy, enthalpy, and entropy, especially for ideal gases, or at least, substituting in an equation of state, like what we're doing on the homework, applying the equations, right? You should be very confident on how to apply these, right? We put them in conjunction with an energy balance or an entropy balance to solve for heat or work or phase changes in the case of fugacity. But we've basically done everything. We've rederived everything. Now, we're not going to leave classical thermodynamics. We're going to go through a couple of different phase equilibrium applications: vapor-liquid equilibrium, ideal, non-ideal, flash calculations, liquid-liquid equilibrium, and then we'll touch on chemical equilibrium as well. But the foundations of thermodynamics we'll have completely derived by about Wednesday. All of classical thermal. Then we'll go through some applications, specifically spending more time on the applications of the phase equilibrium, and then we're going to move on to statistical mechanics, probably around mid-October. Okay. So, we're going to derive some additional relationships for single component systems. We're going to start off with the Gibbs phase rule. So if I have water at various temperatures and pressures, let's say it's 20 degrees C, and this is in units of atmosphere, and 1 atmosphere. This is all the information that I need to know to fully describe the fluid. We know what phase is this in. 20 degrees C and 1 atmosphere for liquid water. Well, it's liquid, I gave it away. Same thing here. If we said it's 150 in 1 atmosphere, we know it is a vapor. If it's negative 20 in 1 atmosphere, it's a solid. So for a one component system, one component, one phase, we have effectively 2 degrees of freedom to fully describe the system. Now, let's say we have a system where we have multiple phases in contact. I have a box, and I have single component but broken into 3 different phases. And this can only happen for a single component at the critical point, the triple point. But it's a useful generalization approach. But assumably, if we didn't know any better, and actually for solids, we can have more phases for solids because different crystal structures, you can sometimes think of them as different phases as well. So for an arbitrary number of phases, so P, we're going to use as the variable for phases. For P number of phases, if it takes me 2 variables to fully describe each individual phase, that means the total number of degrees of freedom for a multi-phase system is going to be equal to 2 times by the number of phases, but minus the number of dependent equations. Right? Or dependent variables. How many of these things are related? Okay, if my 3 phases are all in equilibrium, what are some variables that are linked that we've talked about? What's constant across all the phases?
Temperature.
Temperature. So we have thermal equilibrium, in which case the temperature of phase 1 is equal to the temperature of phase 2. Temperature of phase 1 is equal to the temperature of phase 3. Now these equations are the two independent. If we added a third one here, where the temperature 2 is equal to the temperature 3, that's a dependent equation based on those two already. Right, so if I added these two equations up, you could get temperature 2 is equal to temperature 3. We have mechanical equilibrium, where pressure of 1 equals pressure of phase 2, pressure of phase 1 is also equal to pressure of phase 3. And last we have our chemical equilibrium, where the Gibbs free energy of phase 1 is equal to the Gibbs free energy of phase 2, and so on and so forth. So this, I get one equation for every two phases that we get. Sorry. I have a relationship between all the different phases, so I have P minus 1 equations here. If I have one phase, I get no dependent equations. If I have two phases, I have one relationship. If I have three phases, I have two of these relationships. So this gives me P minus 1 equations. Same thing here, P minus 1. Number of phases minus 1. So I have 1, 2, 3 times these types of different relationships. So if I go back to my Gibbs phase rule, the degrees of freedom, we have 2 variables for every phase that's necessary, minus 3 of these equilibrium expressions. So if we do the arithmetic, the Gibbs phase rule for a single component system is equal to 3 minus the number of phases. For a one component system. And then when we transition to multi-components, we'll of course revisit this concept. So let's do a quick double check. If I am in vapor-liquid equilibrium, how many phases do I have? 2. How many degrees of freedom do I have?
1.
So that means I can fix one variable. If my system is in vapor equilibrium, I have one variable I can change. I cannot change the temperature and the pressure independently. If I change the temperature and I say it's got 2 phases, that means I know it's the saturation temperature, which means that there must be only one position for the pressure. If I have the triple point, how many phases do I have?
3.
In that case, I have 0 degrees of freedom. I cannot control what the triple point is. That is already defined based on the fluid itself. I guess you can kind of think of the critical point similar to that too. Right? You can have vapor, liquid, and supercritical fluids. That would be locked in. So the critical point again is locked. So this tells me how many phases I have, but it doesn't tell me how much of each phase that I have. All right, so let's say we have water. I say it's in vapor-liquid equilibrium, and its total enthalpy is equal to 2,000 kilojoules per mole. Oh, kilojoules per kilogram, sorry, that's what the units are. And this is at 100 degrees C. So in this case here, the system, this tells me that I'm in vapor-liquid equilibrium, right? Because I've defined that I'm in 2 phases at 100 degrees C, so it's kind of locked my position. But what it doesn't tell me is how much of the liquid and how much of the vapor that I have. So we need additional relationships, and we need additional relationships of the form like this one here. Now we'll be doing this notation a little bit. So this could be, let's see, no, not that. Yeah, I can do that. U, H, V, S, so on. units don't work out for this. This needs to be mass, actually. Mass or number of moles. Or we can think of this here. Let's see, not mass times specific. Hold on a second, I think my units all messed up. This is this is specific, so this is energy per mass. Energy per mass times a fraction. No, sorry, this is fine. In this case here, omega I is equal to mass fraction for this particular example. So to know the quantity in each phase, we need additional expressions. We need an expression for each phase minus 1, noting that this omega I is equal to the mass fraction in phase I. There we go. It's more clear. So if I know the total enthalpy of the system, then I could look at the individual specific enthalpies of each of the two phases and use this information to figure out how much material is in each phase. Or that could be the total density of the system, or the total volume of the system. Right, so the P minus 1 is for all of these expressions. So if I have lots of different phases, I might need to know two properties, enthalpy and the volume. But then you've always got this last expression here where the fraction in each phase has to add up to 1. There's a consistency relationship. So in this example up here, if the enthalpy of the vapor and the enthalpy of the liquid are found in the steam tables for this set of conditions here, the liquid enthalpy is 419, and for the vapor is 2671. We can apply this expression here, where we're basically taking a weighted average of how much the liquid enthalpy is bringing to the mixture and how much the vapor is bringing to the mixture, in which case we can then solve for the weight fraction in the vapor and liquid phases. For this particular example, it would be 0.298 and 0.702. And with this information, we basically fully describe the system for a multi-phase, but single component system. And we can repeat all this, of course, for a multi-component system. It gets a bit more complicated.
I have a question.
Yes?
Do we not need to know the pressure to get the enthalpy from a table?
We would be able to look up what the pressure is based on this information here. So if we know that water is in vapor equilibrium at 100 degrees C, that fixes our position in space. So when we're in vapor-liquid equilibrium, we have two phases, 3 minus 2 equals 1. The one additional variable we define is the temperature. Okay. So a few more relationships to kind of round out our discussion of multi-phase systems. We have to, of course, derive the Clapeyron and the Clapeyron equations. So, at equilibrium, between two different phases, the Gibbs free energy of phase 1 is equal to the Gibbs free energy of the phase 2. We can differentiate these expressions. And then we can substitute in our state change properties that we derived from the combined first and second law. And of course here I'm recognizing that pressures and temperatures are the same across the two phases. So if we rearrange this expression and we solve for the change in pressure with respect to temperature while holding the Gibbs free energy constant, which is going to be the case as we go across to phase transition, we can rearrange this expression for each of the two sides of the equation, and what we find is that we get that we can relate between the entropy and the volume change to look at the pressure. Now we know that this is the vapor pressure as well. The saturation pressure is a more generic expression than the vapor pressure is, because you could have kind of a saturation pressure for a sublimation process. So vapor pressure kind of, well, so yeah, these kind of are interchangeable. Saturation pressure is kind of the more generic. So from the expression as well, we could also rewrite this knowing that the Gibbs free energy across the phase transition is 0. So we can rearrange this expression to demonstrate that delta S, the change in entropy, is equal to the change in enthalpy divided by the temperature. We can then substitute that expression up into here. And then we get the, and this is what we call the Clapeyron equation. We've already applied this in homework 1 to understand how to relate between the enthalpy and entropy of sorts when we go through the phase transition, when you guys built that enthalpy table for toluene, I think it was. So what you can use the Clapeyron equation for is that if you can measure, if you know you're in multi-phase system, vapor-liquid equilibrium, you can just measure the system temperature and pressure and use that information to find your heat of vaporization. And that's oftentimes what's done. And so if you know your system's in multi-component, multi-phase system, you know its temperature and pressure, then you can use this information to calculate the change in enthalpy or the change in entropy. And so instead of having to do more detailed calorimetry experiments, we can just measure the pressure and temperature on the system. Now, if the vapor is an ideal gas, and we assume that the specific volume of the vapor is much, much greater than the specific volume of the liquid, that means that the change in volume is effectively just equal to the vapor volume, meaning that we're totally neglecting the density of the fluid itself, noting that a liquid density is much, much smaller than the vapor density. If we do this, we can substitute in the ideal gas law. Yes, that was right. Okay. These are two different forms of the Clausius-Clapeyron equation. All that was done was I substituted the delta V for the volume of the vapor, which is RT over P, following the ideal gas law. And then this one here is one extra additional trick that I'll talk about. So this is something that we'll see oftentimes in thermo. Now, this expression here, if we assume that the delta H of vaporization is approximately constant, meaning that it's not a strong function of temperature, which it is a function of temperature, right? But for over short distances, we can partially integrate this expression, right? So if the heat of vaporization is approximately constant, what we can do is we can integrate it from T1 to T2. So if we partially integrate it, what we see is that the vapor pressure is an exponential function of temperature. And this is why we have the Anton expression having a very similar functional form. So in Anton's equation, we have an exponential function. We have the temperature in the denominator that exactly follows the functional form that we see for a theoretical vapor-liquid phase transition as well. So the Anton equation is chosen, the functional form is chosen because it matches theoretically the true functional form that we would expect to have in a system, in a real vapor-liquid equilibrium system. So they selected this to correlate and fit the data because it has the functional shape that seems to work the best. So that's where the Anton expression comes from. So the coefficient A is in many regards related to the heat of vaporization of the fluid itself. Now, one trick that they like to do a lot in thermodynamics is this one here. These two expressions are 100% equivalent. So you can grab this extra dependent variable and kind of combine it into the differential using a little trick. So I just want to go over that really quickly as something that might come up again in derivations throughout the class. So if we generally write any equation, right, dy dx, if we say this is equal to y, like an exponential would be an example here. We can do substitution, where we define w as the natural log of y. So that if we take the derivative of w with respect to y, it gives us 1 over y. Then if we solve for dy, this is equal to dw times by y. Substitute it back up into this expression up here. Y dw dx is equal to y. These cancel out. Or in other words, d ln of y dx is equal to 1. So it's just a little calculus trick that people like to play in thermodynamics. This is, I don't know, this is very common because it reduces the complexity of the equation a little bit. where you don't have to deal with another dependent variable on both sides of the equation. But it's just W substitution. I think this is actually called W substitution, right? That's the term they like to use in calculus. No one remembers their high school calculus? Or college calculus. Okay. One other topic to discuss for phase transitions. So vapor-liquid equilibrium, solid-liquid equilibrium, solid-vapor equilibrium, those are all referred to as first-order phase transitions. Does that term ring a bell? Who's heard of first-order phase transitions? Well, hopefully you start hearing it more and more. So what they mean by first-order phase transitions is that the Gibbs free energy is continuous across a phase transition. So for a first order phase transition, the first derivative of the Gibbs free energy is a discontinuity. That's where this term comes from. So for example, the rate of change of the Gibbs free energy with respect to temperature at constant pressure. This is of course what we see when we're keeping across a phase transition. This is equal to the negative of the entropy. Likewise, if we take the first derivative of the Gibbs free energy with respect to pressure, the entropy and the density are certainly discontinuities when we're going from a liquid to a vapor, right? The density of a liquid is fully defined based on its temperature and pressure. The density of a gas or a vapor is fully defined as a function of temperature and pressure. When those temperature and pressures happen to meet, that doesn't mean that the specific volume of the liquid and the vapor are the same. There is a step change. So if I have a system where I have a phase transition here, right, where I have very dense fluid on one end and a lighter fluid on the other. If I look at the volume as a function of the position, it'll be very low and then jump up and then be higher. Same thing with, or the entropy has the same shape. That's what we call it as a first order phase transition. They also have second order phase transitions. And this is something that as chemical engineers we will very infrequently see, but as material scientists or metallurgical engineers, that can be seen. The second order phase transition is where the second derivative of the Gibbs free energy is discontinuous. In this case, we have, let's take the example of the second derivative with respect to temperature. So this would be an example of a second order phase transition. If the heat capacity has a discontinuity when normalized by the temperature, that's a second order phase transition. And this is something that can be observed, for example, in a quartz solid phase transition. Basically transitioning from one crystal phase to another crystal structure by changing the temperature or pressure conditions. And there have been no phase transitions that have been discovered that are higher than second order. This concept here comes up a little bit when you're talking about some kind of theoretical computational-based physics, because finding a simulation or a function that exhibits this characteristic has actually been very difficult to accomplish. And so if you can model a first-order phase transition and then have a continuous expression that when you differentiate it follows the same characteristics of a real fluid, that's something that people are interested in. Okay, last few minutes of class, I'm going to introduce what we're going to be talking about on Friday. And that is small systems. So as has been mentioned so far, everything that we're talking about is infinitely sized. Now we may not be thinking it's infinitely sized, and the concept of what is infinitely sized for a molecule might be very different than what we consider infinitely sized. A glass of water is infinitely sized because there is a whole lot of molecules in there. And the likelihood or the probability that a molecule is at an interface is very, very, very small. Because molecules themselves are on the order of a nanometer. So if I have a glass of water that's a couple of millimeters across, right? That means that there's, I don't know, how many molecules are there in a straight line spanning between a nanometer and a millimeter? Was that 1 million? So that means 1/1,000,000th of the molecules going across a straight line of a millimeter is touching the wall, on average. I'd say that's pretty infinite for the molecules case. But for small systems, when we start to talk about droplets or emulsions or aerosols or sprays, when we get these colloidal systems down or these droplet systems down to the order of microns or even tens or hundreds of nanometers, you can no longer consider our thermodynamic systems to be infinite in size. And there's a penalty for that. So if I have an interface between two different phases, this could be two different fluids, right? This could be a liquid-liquid interface like oil and water or water and oil, or this could be a vapor-liquid interface of the same fluid. This could be a solid-liquid interface. Any interface between A, which could be the same component or different component, and let's say B. How molecules interact is through binary interactions. At least that's how we model it. If we look at the potential energy as a function of the separation distance between two particles, molecules of type A and A, they'll have some comfortable separation distance that they like to be apart from one another. B and B will maybe have a slightly different way that they want to be near one another. And so how it happens to work out is that A molecules kind of vibrate, their electrons slosh around, they pack together in a particular way really nicely. Same thing with B molecules. They have a certain way they like to interact. They pack together a certain way. Their electrons oscillate and vibrate at exactly the same frequencies, and so they just mesh together really well. So in general, molecules of different types don't necessarily want to be with one another. Now, entropy supports them being together because if some of the A were to diffuse into B, well then that A just gained a tremendous amount of entropy. If some of the B wanted to diffuse into A, it gains a tremendous amount of entropy. Right? So the entropy is what is encouraging everything to mix together. Internal energy, the energy is always minimized when you have phases completely isolated from one another. The total free energy, the Gibbs free energy, is not always minimized when the two are phase separated because of the entropy penalty. So what happens then is if the A, as a bulk fluid, were to try and push into phase B, what I'm having to do is I am creating, right? This is a straight line across. I am creating new contact surface area between these two separate phases. which means that they're not going to like each other. So the act of creating a larger interface is such that it takes energy to do so. So when we're dealing with small systems, this concept is known as surface tension. I don't particularly like the term surface tension. I think it's much easier to think about it in terms of surface energy. Surface tension is back into the historical context where you could see little insects and bugs standing on top of water. That's because the mass of the object and the interface that they created was such that it was more energy to create a full interface, like if this is a spider leg or one of those water skiers or whatever the case is, right? The penalty of creating an interface that's deep enough to cause this creature to sink into the water is more than just having it float on top. So that's what the term surface tension has its history into. But in reality, it's really surface energy. And that costs energy to create an interface. Now, the reason why droplets are spherical is a sphere is the shape that minimizes the surface area to volume ratio. There is no other shape in nature where you can have the same quantity of a material with the smallest interface. So that's why a droplet is the way that liquids like to behave and bubbles like to behave. They're always spherical in shape because that is the way that minimizes the contact between the two different phases. Right, so this is the case when you're boiling water, right? You can have an interface and a surface tension between liquid water and vapor water. You can have an interface and surface tension between an oil and a water-based phase, right? So there's always going to be surface tension between any two phases. So on Friday, we're going to be talking a little bit about this. All right. Take a look at the homework. We can help answer any questions on Friday as well. And if not, I'll have office hours tomorrow from 12 to 2. And then if not, I'll see you on Friday.